Apologies.
Okay, right.
Okay, I'm sorry. Well, I
No
hope my
problem.
voice will work, and I hope that it will be clear, that I'll be able to be coherent. It's 5 o'clock in the morning here, and
Okay. Yeah.
and I'm just delighted to have this opportunity.
Okay.
So I made the title. Oh, sorry. You want to introduce me,
Yeah,
please?
let me introduce you, but briefly. And then I think Dr. Nicola Sereni already said something about ASESMA. So ASESMA is the African School of Electronic Structure, Method, and Applications. And the start of this of ASESMA was through Professor Richard Martin. And there were a few other people, his former postdocs and a few other people that started it. But Richard Martin has been the one person who has spearheaded and has gotten a lot of things going for ASESMA. Okay, so like now the next ASESMA will be in 2025, June 2025 in Ghana. Professor Richard Martin will be there teaching some preschools before then also. So Professor Richard Martin was a professor at University of Illinois at Urbana-Champaign. And then after he retired, he went to Stanford University. And so has affiliations with both UIUC and Stanford University. So we're happy to have Richard here to tell us about ASESMA, about DFT, bringing together physics, chemistry, material science, biology, and other fields. Okay, so over to you, Richard. Thank you.
Okay, thank you. So I made a different emphasis in this talk than I have some other times. Let me start with something about ASESMA. And Nicola may have already told you this, and I'll say it again. It's a 10-year program that was started in 2010 and with a preview in 2008. The 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 great thing that got it going was first Nithya Chetty in South Africa and Sandro Scandalo at ICTP, and me helping is what got it going. And then the IUPAP, that's International Union for Pure and Applied Physics, was endorsed it, and that put it on the map. That it's a real program that keeps going, and so it's now a series of schools, and the second decade was also endorsed by IUPAP because of its the success of the first years. And the idea is to move on, to always be doing new things and keeping up with the field and generating new activities with this nice name, the Assessment Galaxy, for different things that are happening more than just this 2-week school. So the next, as Omoloru has said, the next school will be in Accra, Ghana, and that's in person. But for the first time this year, we are having a new preschool, which will be online, and it's starting February 20th, and it's to help people get started in the field. So if you're new in the field, the purpose of this preschool is to help people get going and be able to get the most out of a school, and starting into the field. Okay, and I'd just like to emphasize the key to all this working is this long-term support from ICTP and IUPAP, and that's going to be the key to keep it going in the future. So the new emphasis for me to make this time is bringing together physics, chemistry, material science, and other fields. This was not exactly the goal at the very beginning. The goal was to find an area that would be important and would be able to bring people together and work together and create a network that would extend across Africa and connect to the rest of the world. And then what I found, which I didn't realize at the beginning, was it was working with the people working together. That was the things that really makes it work. And so working together with a vision of appreciating the different fields like physics, chemistry, material science, and other fields, and working together was such an important thing. Now, each of these fields is important in itself, and it has its own challenging problems. And I'm not trying to supersede any of that. To be a good chemist or to be a good material scientist, you go beyond what's in this school. You go beyond theoretical physics, but there's a core that we can work together and help each other. And we have chosen the core that's the most fundamental level, which is the properties of molecules and materials determined by quantum mechanics and the electrons that hold the material together. So the basic problem is a true grand challenge, the electronic structure problem. It affects all these fields, and it's a grand challenge because it's so difficult. And that's why it's not just solved. It's it's what causes that there are really so many properties, so many various materials, so many things that are created from this system of electrons and nuclei. And another thing is that we've now, with computers, gotten to the point where we can do realistic problems and not just textbook problems. And so having the abilities to do the calculations, which is one of the important things of ASESMA, is just a key to the problems. So one of the things that's happened that's really come to the fore in the last decades is that theory and experiment can work together in a completely new way. It's very important for us to have to learn from one back and forth. Theory and experiment taken into account, or attempting to take into account problems that will really affect people that are important. So here's the goal then, that we're attacking a difficult grand challenge of physics. It's on the level of the most difficult, most interesting problems in all of physics. We know that computation is an essential part of the problem. And of course, this very special thing about all these fields is that it really is, there's real things happen. And so experiment and development are essential. So I mentioned DFT in the title. DFT is something that's truly enabled a revolution in how theory and experiment can work together. And that's one of the main motivations for ASESMA and main things I'd like to bring out in this talk. Okay, what's ASESMA do? This is from the start. It was recognizing that computational science is important. And we and you, most of you people on this talk, are either students or teachers, and we know that we need to be effective in teaching the other students and in learning, and computation is just an important part of that. So we're going to need to work with computer programs and the advances that have been made possible by computers. So what should we study out of this enormous range of things that's for this grand challenge of physics and the enormous number of properties in chemistry, material science, etc.? The electronic structure was chosen because it's an important field and it's narrow enough that people can work together and build up the network for collaborations. And yet it's important enough to actually have these very many applications and bring people together. So a typical ASESMA school has features that involve lectures and hands-on and projects. And typically there are half of the participants are new to the field and half are returning to increase their knowledge. This is really important that people return, because this is how you build up the network. So it's not just a matter of starting in a field, it's a matter of continuing in the field and the and building it up to a lifetime of research. Okay, so here's a typical ASESMA school, and here's the things that go on. Density functional theory is, we'll describe later, is the key method that's being used because it's made so many things possible. But we go on, and in the projects, we do things like quantum chemistry and molecular systems, and we have great lecturers like Mark Casita, who was the pioneer of time-dependent DFT, and he is very active in projects and in lectures. At the right is one of the students from Ghana that was chosen the best students at that time, and she and others have now gone on to work with Andrea Marini and Matteo Gatti, and this is methods that do methods, but the starting point is a density functional, so it's really essential for the kind of progress. The last school had machine learning as part of the school. So we stick with fundamentals and we move on to things that are really the most current in research. So here's the history. The ASESMA has been in all of these different places. The idea was to move around to make it more accessible to different people all around the continent. And it's grown into things like mini workshops that are in more places, and sessions at meetings like the African Materials Research Society. So this is what's kept it going, and this is what's made it possible to have almost 300 participants over these years and build up active research groups. So these are places where the students have come from during that time. Each dot represents often several different universities in the same country. So there's more places than actual dots that's on this map. And this is active research groups that have grown up. This is a partial list, and my apologies to someone that's not on here. It's not, I don't know all the groups, but I do know many that were started by ASESMA, and many others that for where ASESMA is a help, but it wasn't the initial start. So I just want to emphasize, these are groups with capable scientists on a world-class level, and they're the teachers of our future scientists, so they are important for society. Okay, now what's the science that we want to cover? As I've said many times already in this talk, we're starting with something that's a really grand challenge. It's one of the basic fundamental areas of physics, and it has these important consequences. I mean, literally, people work on starting from the basics, go all the way to projects that involve solar energy, or batteries, or catalysis, nanosystems. They're literal calculations that are helping understand the work in all of these areas. And I'll give a few examples later. But first, I want to emphasize what a grand challenge this is. Until the 1960s, there really was not even a clue how one would make calculations for real materials in an accurate way. And if you want to make progress in these important problems, you have to solve things accurately. You have to be able to tell that one molecular structure is more stable than another. But you have to be able to tell how atoms move in a battery. You have to know the band gaps and the absorption of photons and how the electrons respond for solar energy. You have to be able to deal with tiny systems and like nanosystems where experimentalists don't know where the atoms are. It's only the theorists that can say the atoms in this particular very small system are making a certain structure, and then it will have certain properties, and then that can be checked by experiments. So, from the 1920s, when quantum mechanics started, within a few years, basic methods that we use today were developed. But those very smart people realized that it was not just a matter of the things that they could do at that time. There was, you could solve the hydrogen atom. You could solve the one electron with two protons, the H2 plus. And with a great effort, there was solutions for two electrons in helium already in the 1920s. But there was just no notion of any way that you could do a quantitative calculation for real material, like silicon, or a nanostructure made of silicon, or a magnet. The ideas were already very well developed in the 1920s and 30s, but not the ability. And it was in 1964 was the advance that made possible accurate calculations. And it was a new idea. So why is this so hard? The many-body problem requires that you solve the many-body Schrodinger equation. Now let's see what that means. The Schrodinger equation is basically written with the parts that are listed below. This is the only equation I'm going to give in this talk. So let's see to be sure we understand what it is. This is the wave function. That's a function of the coordinates of all the electrons. The operator that operates on this function is a derivative, second derivative. That's the kinetic energy, and it's the sum over all the electrons. And they're in the presence of the nuclei, so this is a potential that these electrons are feeling. And if there were no electron-electron interactions, we could solve the problem. We could solve the problems with the methods that were developed in 1920 and some of the classic ways to improve the methods in the 1930s. And the only thing it was missing at that time was computers to actually do the calculations. So if there were no interactions between the electrons, they would just be independent, and it would be a matter of just you solve for the different states that the electrons could be in, and because they obey the exclusion principles, the electrons, well, we could calculate the different states and populate them with the electrons, and it's a soluble problem. It's you can do it analytically for one electron, and with computers, you can now solve with many electrons, thousands. So it isn't the fact that there's many. Problem is that they interact. Because of interacting electrons, the problem is really difficult. You might know of the problem of gravitation, that the three body, just only three bodies moving with attractive with the gravitational field is not a solved problem. Quantum mechanics is solved in ways that are somewhat easier than that in some senses, but nevertheless, the soluble the solutions can be done even with the largest computers we have today with only a few electrons, maybe 10, maybe I'm not counting right, maybe 12, but it grows exponentially, and it's just not something that you can just solve. So what do you do if you have a molecule with 50 electrons? What do you do if you have a solid with 10 to the 23rd electrons? Now, you may tend to make different approximations or different ways of approaching that problem if you have this huge number like in a solid, or you have a finite number like in a molecule. But nevertheless, it's the same problem, and we would like to attack it in as much as possible in the same way. So density functional theory is what was invented in 1964. I use the word invent because this was very clever assertion of a new way of doing this and very difficult problem. The statement of this Hohenberg and Kohn theorem is that everything about a system is determined by the gravity density is just a function of three variables. So it's just a function in space. Now, how could this possibly be true? Well, the answer is that first you look at the Schrödinger equation. All the properties are determined by the potential. The electrons in all materials are the same mass. The kinetic energy operator is the second derivative of the wave function. What's different is where the nuclei are. And so if you know where the nuclei are, you know the potential the electrons are in, and in principle, you can solve and you can get any property. But the problem is that Schrödinger equation in principle, but in practice, you just can't do it. So let's keep going with the idea that in principle you can. What Hohenberg-Kohn showed was that there's a one-to-one correspondence of the external potential and the density. That means that if you choose a density, there's only one potential that could give that density. And therefore, it's really a small statement. The potential, if you know the density, there's only one potential. And if you could possibly solve the Schrödinger equation, then you would get any property. And the word functional is that you have to know the density everywhere. So it's a function of a function that to get any property. But the theorem doesn't give you anything, but just go back to the original problem and solve it. You in principle go from the density to the potential, but then you're left with the original problem. Do you think that was worth a Nobel Prize, which Walter Kohn got in the 1990s? Probably not. That was it. That was the idea of Hohenberg and Kohn. But the thing that was worth a Nobel Prize was what Kohn and Sham did in constructing an auxiliary system, not the real system, but the auxiliary system. And we've already said that if the electrons were independent, you could just solve the problem. And in practice, you can solve the problem. And so Cohn and Sham propose that we'll construct a independent particle system, not the real problem, but one that's designed to give the real density and the real energy of the real problem, the hard problem. So you give up the idea of solving everything about the original hard problem, but you design a way that you can get some of the properties of this real system in a way that turns out to be really practical. So all the hard parts of the problem are buried in a functional, which means something that if you knew it, you would be able to start from the density and get the hard parts of the problem. That's called the exchange and correlation among the electrons. And if you added that term to what you would get for the independent particles, that you would get the solution for the energy and the density of the real system. And in practice, what that means is you just still don't know that grand functional, but the thing it turns out is that you can make good approximations. So we have a system that's buttressed. It's, the fundamentals are determined by this Hohenberg-Kohn theorem. And so we've got a theory that we know in principle what could work. And the challenge is to find good approximations that actually make very useful results. And it turns out that's what you can do. The first simplest functional is the local density approximation that was already suggested by Cohn and Sham. And then there's many new improved approximations later. The local density approximation is just saying that at any point in a real material, this density that's due to the fact that the electrons are not independent, this energy, I should say, is the same as if it was in a homogeneous electron gas. Now, there have been good calculations, many body calculations for that system. So the approximation, excuse me. Notice my cup. It's magic that works. But then you start looking at it and there's reasons to understand how it actually works. And there's reasons to understand how you start making improvements. And so with the improvements, it's now truly an essential part of research. And it's really useful. With density functional theory, you can calculate lattice constants of materials. Silicon with 1% accuracy, iron, a magnet with of order 1% accuracy, the much more complicated structures with accuracy at that general level for where the atoms are. And that's the starting point for understanding other things. For phonons means the vibrations of the atoms within similar accuracies. So the structures and properties like vibrations, you really can get with just amazing accuracy. And it's a useful approximation for other properties, and it's a starting point for almost everything else. If you look at any quantitative theory of material, from the high temperature superconductors to semiconductors, the starting point is density functional theory. So I'd like to give you some evidence of how important it is. So the Cohn-Sham papers are among the most referenced in physics. I think it's the most referenced in physics and among the most cited papers in science. It's truly transformed research. There's approximately 50,000 papers a year written using density functional theory. And that's a realistic number. In 2010, well, a little later, around 10 years ago, there was a real study that was counting papers, and there were like 30,000 per year then. So almost certainly it's more than 50,000 papers a year now. So I did my own little survey to get a sense of what's important, and because it's not just numbers, it's not just 50,000 papers, it's that each one of those was doing something. So I looked at the magazine that I subscribe to, the Science magazine, which is the main journal in the United States. It covers all of science. The main journal in Europe is Nature, and the results are similar for Nature. So these are the journals that have articles on biology, chemistry, ecology, medicine, neuroscience, uh, uh, elementary particle physics, condensed matter physics, all fields of science. And I've given talks like this quite a few times, and each time I've looked in Science magazine to see what was the most recent things, how much was density functional used. And here's what I found in the last 3 issues that I looked at for Science magazine this month. 5 papers that reported work on atomic scale research. I mean, that's getting down to the real basics of materials. That would be molecules and solids. And all were experimental papers. None of these were theoretical papers. The main part was the experiment. And theory as a part of the research. And in every survey I've done in recent years, more than half the experimental papers at this atomic level use density functional theory. So it's useful. So let's see some examples. This is what I found in the last papers this month. Here's a paper about how to make efficient perovskite solar cells, and they're the most efficient and the easiest to manufacture cells that there are nowadays. But the problem is they're not as stable as silicon or some other system. So this is putting film on top of the perovskite cells to increase their stability. And look at this figure from that paper. This is putting how you actually put another layer on top of the perovskite, and voltmeters that look like from an undergraduate laboratory. That's might look like the last place you'd find a theoretical physics paper. But you look in the text, and we perform first principles density functional calculations to investigate the phase transition. That's basically what happens to this molybdenum disulfide when it's put on top of the perovskite, and that's you need this kind of theory to get at what's really happening to systems like this. Here's another one. Mechanically robust and stretchable organic cells for things like wearable electronics. Here's a figure that shows this piece of electronics put on a finger and bent, or something that would go on your wrist that would pick up the signals from your body. And this is a particular paper was interested in organic solar cells, but using particular molecules or adding molecules to this organic system to make it more flexible and to still have the good electronic properties. Well, look in the text. DFT optimization of donors and acceptors for these small molecules that you added was done with some of the recent developed the calculational methods. Jaguar is just one of the codes that's available. It's just a different way of doing the same calculations as the quantum espresso code. That's the main thing used in ASESMA schools. And using functionals, that's just like you can use that same functional for solid or for catalysis. In fact, it is used very much for catalysis. And here it is, understanding molecules that help make the organic electronic systems more flexible. Here's two other papers that these look like a more things you might expect to need the theory for. This is the actual positions of atoms in a zeolite, which is one of the main catalysis systems that they use throughout the world. And this is, so in this case, you're really looking at where the atoms are. So you might expect the theory to be important, and it is. The actual experiments use neutron scattering and magnetic resonance, but they did it along with density functional theory to put together what was really happening. Here's a particular phase of a system that's a candidate for solar cells, and they use density functional theory to gain insights into the processes. So it's really useful. So let's now be sure that what it was, though. Cone-Sham is not the same as Hohenberg-Cone. It's amazingly good for these things like the structures of systems and the vibration frequencies, stability. But it was designed to give only the total energy and density. It wasn't designed to give everything. It turns out that often some of the properties that you might think, if you just use it where it shouldn't be used, you often get bad results. But nevertheless, it's still the starting points for other methods, and it's exactly still important if you need to if you want to do a better calculation of things like optical properties. So there's so many interesting problems, and DFT has turned out to be the great advance that's made it possible to do so many things and to get started on the grand goal of being able to calculate many properties and make it more and more useful. So this is a slide I showed you before, just to reinforce that the idea for density functionals is to get the really firm background on what's needed. So you need a basis and not just jump into other more advanced things. But ASESMA is designed for new people to get started in the field, mainly with density functional theory, but to also provide opportunities for more advanced people to work on advanced problems of molecular systems, catalysis, solar energy, and to use more advanced techniques and to learn about things like machine learning. So it's both, and that as part of what's important for current research and development in science. Okay, so early on I mentioned working that it's important not just the research, but working together. If you want to be an active researcher, you must keep up. You must learn from others. You must learn and be a part of local and regional and global science communities. walk down the hall and talk to people in a different field, and and make connections to get ideas, and look for science that's going on and in the world, and get ideas. You really need to be part of the global community and the local community to do the best work. And it's not just the ability to do a calculation, it's ability to know what to do the calculation on and to understand what's happening. So that's what ASESMA is about. So be a part of the ASESMA network. Here's a website that tells you more about it. Learn about some of the other things like ASESMA. That's a program that provides mobility for people within Africa and support travel to meetings in Europe. And there are calls for that you can find with, and the information is at this website. Go to or apply, I should say apply to go to the next school. It's a competitive process. Many, many more people apply than can be accepted. So one of the things that we're doing this year for the first time is to help people with little experience get started in a preschool that's online starting February 20th. The idea really is that if you're new in the field or don't have much experience in the field, that this would help you get going. And by doing showing that you've done a good job, really what I mean is you followed and asked questions and were an active participant in the preschool will be an important aspect of being accepted for the main school that's in Ghana in June. I'm going to come back to that as a summary in just a minute, but let's see what the time is. Okay, I think we just have time since I started late. Sorry. I want to do this quickly, but it's something that Omalolu, Professor Akin Lojo, asked me to answer. Most of all, I'm asking you to follow your own interest and keep in mind what's realistic for you. Let me mention what happened to me in my college and early years in graduate school. I started electrical engineering, and I loved it. It's very practical things, and think that if I were studying electrical engineering now, I might stay because there's so many interesting things going on. But I wound up in theoretical physics because I found that for me personally, it was these basic ideas that was just the most interesting, and so I followed that path. And now looking back on it, I realized that I could follow that path because of great support I had. It was called, I was right at the end of this golden age of science in the United States because there was so much money and put into it after World War II and growing universities and all that. I was at the end and I almost didn't get a job. I got one job offer because I was a little bit too late to be at the place where there were plenty of jobs. But when I look back on it, the most important thing was not that I knew how to do some particular calculation. It was being in places with active, smart people that gave me the impetus to continue. So if right now, if I were starting, my goal would be to be with active, smart people. And I'm delighted that the virtual communications gives you more options. You don't have to be in a particular university to get particular interactions with people, or you don't have to be at the very best meeting. if you can't be there, there's a lot of ways of being in contact through the literature, through virtual communications. So there's some options available that wasn't available to me when I was starting in the field. I would try to learn about things like machine learning and artificial intelligence, but I, I would either try to do them well, or I would try to understand other problems well, and keeping in mind how machine learning or artificial intelligence could be important for my field. But most of all, I wouldn't try just to get results. I would try to understand whichever the problems that I would choose. So I'm going to go back. Oh, well, first of all, this is an acknowledgement to all the support we've had for ASESMA, which has just been wonderful. And I want to go back to this slide and leave it up as my conclusion slide. Okay, I'd like to stop now and ask any questions. People still there?
Yes, okay. Thank you very much, Richard. We appreciate this. Yeah. So if you have questions, I'm sorry we started late, but we'll take a few questions and then we'll try to end maybe in like 10 minutes. So if you have questions, you can unmute yourself and ask, or you can type it in the chat and then we can ask Prof. Richard. You can unmute yourself if you have a question.
Can I see the chat myself without stopping sharing?
Can you what?
See chat with, do I have to stop sharing in order to see the chat?
It depends on, okay, yeah, you may stop sharing.
Okay, I think I have to do it.
Okay, yeah.
Okay, so reactions, participants.
Maybe I have a question. When you started, it really, I mean, were you kind of foreseeing that the thing would be so successful? I mean, if I look back at what was possible in the years when you were young, I mean, it really looks like a very fundamental thing, but very, very far from really studying any real material, right? Or were you optimistic, or you were just interested in understanding the basics and you did not what was the situation then? How did you see it then?
So sorry if I'm being there. Now I'm back on that. I can see you. Actually, my thesis was something that you might consider really mundane. It was the lattice dynamics of silicon. And I was solving 8x8 matrices, and I had to turn in decks of cards with overnight calculations. And it was a free version of Fortran called Fastran at the University of Chicago. And the idea then was to try to figure out what were the electrons doing, and how did you describe a bond, and how did you describe some of the features that were unique for silicon. And you can see motivations already for understanding why you would want something more quantitative. So exactly the same problems are what we can deal with routinely, and which quantum espresso does just very, very well. But I did something else that kept me on a track that was not just the quantitative calculations, but it was keeping in mind that it was a many-body interacting problem that had all these features. That's all the wonderful properties. And I worked on problems like the Kondo effect, which is one of these many-body problems that was where you just the ideas, just how did it work was the important thing. And for me, one of the properties that was super important was the Luttinger theorem. Does anybody know on this slide know what that is?
Did anybody know what?
What the Luttinger theorem is?
The what?
The man's name is Luttinger, and he worked out.
Oh yeah, I know the Luttinger theorem.
Right, a theorem on
Okay,
properties of materials. What the theorem? It's not really a theorem. It's a assertion that's backed up with mathematics, that the volume enclosed by the Fermi surface of the real honest system, the real many-body system, is the same as the independent particle system. As a well-chosen independent particle system, it would be something that has the same symmetry and things like that. That the volume is the same. For me, that was one of the absolute keys to saying that something like the Cohen-Sham calculations for materials get the properties of real materials. So when you come up with a Fermi surface, you know something about it should really apply to the real system, even though you're making approximations with which function. So I followed basically two paths, and that was the thing that kept me going all this time. It wasn't two paths. I made them one path. That was the important thing.
Yeah. Thank you very much. Richard, there's a question. Somebody asked a question about the accuracy of DFT. So the person said, I'm worried about the approximations. Can we really trust the accuracy of DFT?
Yes.
How accurate is
let's see.
Out of 100? Out of 100. Yeah.
Sorry for my being just really silly. I know that this is done, but now I can't find the. Oh, well, please repeat for me any questions that are on the chat.
Yeah. But this is the
I
question.
Can't see it. Okay, I'll just say it's DFT as practiced has approximations. You can't just believe it. You have to do the calculations well, and you have to have some knowledge of how good is the approximation for the functional that you're using. And that's experience. I don't think there's anything there's not mathematics that says you should get the lattice constant in 1%. It's not mathematics that shows you should get the phonon frequencies within 5%. You need experience for your own experience, and then learning from others for what should work under what circumstances. Like those molecular systems that I mentioned that were in this month's Science magazine used functionals that were particularly designed to work well for molecules. They actually work well for solids too, but they're functionals that are just more expensive to use for solids, so people tend to use different ones. But keep in mind that there's one basic theory that's being used, and then you have to adapt and be knowledgeable about how it's being used and what you should believe and what you shouldn't. So it's really good, but you need to be knowledgeable. Other questions?
Hello, Prof. Hello.
Yes.
Hello?
Yes.
Yeah. Can I have one question?
Good.
Yes.
Yeah. So I just would like to know, like, how the DFT calculation we are doing now, this electronic structure calculation and others, will be affected with machine learning predictions. Will it be replaced or will...
There is going to be an effect. Let's just say that. I'm not able to predict just what, but almost certainly we'll learn new functionals and learn how to calculate things at this atomic level better. But what I'm imagining this, but you have to learn. You may know more than I do, and many, or somebody on this screen probably knows more than I do of how we use it for going to more complicated problems. Basically, that the density functional theory is, as even though you can do 1,000 atoms on a very big computer, or 100 atoms on a small computer, even a laptop, it's still limited. To get real thermodynamic properties of materials and treat very complicated systems, it's much better if you have information that's been trained on density functional theory and then more quickly apply to very complicated problems. So if you look at what's done with machine learning right now, and it's learning from the large numbers of density functional calculations that people have done, and then applying that to more complicated problems. Okay.
Okay, thank you, Prof.
Yeah. So thank you very much, everybody. So this series will take place every month. We'll try to make it the last Thursday of every month. We thank Professor Richard Martin for starting this one for this month, and then we'll let you know the topics later on as we go along. Okay. There's information on our website, the ASESMA.org website, so you can visit the website, and we'll update the information from time to time also. Okay. I put in the chat Professor Nicolas Seriani's email if you want to know more about the preschool. And also, if you want to contact Professor Richard Martin, his email is also in the chat. So, and also, if you visit the website, this would be fantastic. Okay. Thank you very much, Professor Richard. And thank you very much, everybody. And we'll meet again for the preschool. We'll meet in Feb, and then at the end of Feb, we'll meet again for the next one, the next lecture series.
Okay, everyone. It's a delight to be able to give a talk, and a delight to see how many people are there. So yeah. Best wishes to you.
Yeah, thank you. Yeah.
Okay.